Thank you, Yorgo. Hello, everybody. So this will be an introductory talk for Logic for Knowledge Representation. My name is Manolis Koubarakis, and I'm a professor at the University of Athens. First of all, let me ask you a question. How many of you have taken a logic course, but not part as AI, logic programming, databases, a logic course? Okay. And now how many have taken a logic course in any sort of form, or like as part of an AI course, a proper logic course, logic programming? Oh, so we still have some people that will learn something new today. So my talk, the outline is I will introduce first of the logic, one of the, probably the most famous logic that we can use in AI, then description logics, and then I will talk about ontologies and knowledge graphs that are essentially, let's say, practical things that are based on logic or are somewhat based in logic. And I'll close with some open research problems that have to do with knowledge graphs only. I mean, I'm not giving like the whole picture for everything, so I will just conclude with some open research problems. Okay, so I claim, and this is what I tell my classes at the Department of Informatics and Telecommunications, University of Athens, all the time, that logic is the calculus of computer science. At least for me, the kinds of things that I have been doing over many years. So not just of AI, but of course it's the symbolic part, right? And in the next talk, you will see how the neural part also comes together with the symbolic part. But this talk is about the symbolic part only. There are many logics that I could present to you, very useful ones, also for knowledge representation, but I will present only one, first of the logic, and then a particular description logic as a means of telling you what the description logics in general are, and then ontologies and knowledge graphs. Okay. So if you want to introduce a new logic, the first thing that you need to say is you have to explain the ontological commitments of the logic. Like, what kind of worlds can it represent, okay? And then, of course, you have to define the syntax and the semantics. The syntax basically tells you what you can express, how you can write it, what is well-formed and what is not well-formed. And then the semantics ascribe meaning to formulas or sentences, okay? Very straightforward. So what are the ontological commitments of first-order logic? If we want to use first-order logic to do knowledge representation in a domain, for example, the domain of summer schools, let's say, then we assume immediately that summer schools, the world, right, consist of objects. One object, for example, is the speaker Manolis. Another object is the talk of Manolis. Another object is this lecture hall, okay? Objects have properties. So Manolis gives a particular course, for example. And objects participates in relations with other objects. So the property was the fact that I'm a professor, right? And I participate in a relationship with the course that I teach, okay? And now, this is important, the relations either hold or do not hold in the world, okay? So there's no, like, fuzzy logic, for example. Or you cannot express probability. You cannot say 80% the probability of this happening is 0.8. Okay. Now some very basic stuff. What is the syntax of first-order logic? You can have parentheses, you can have the logical connectives, you can have variables, you can have quantifiers, you can have constant symbols. So if I want to refer to a person who is called Yannis, I might introduce a constant symbol John. Okay, if I want to talk about numbers, I have to introduce them, like 5, 6, etc. Then I will use the equality symbol. Predicate symbols, so maybe I would like to talk about people that are happy. I have to introduce a unary predicate happy. I want to talk about brothers of people, so I will introduce a binary predicate brother. I want to talk about when people arrive where. I use a ternary predicate arrives. And there are also function symbols. I might want to say that somebody is the father of somebody else. Okay? So this is like a predicate, but it's functional. Now, from constants and variables and function symbols, I build terms. So I can say, for example, John. I can say X. I can say father of John. I can say wife of father of X. Okay, as big as you want, terms. And then from terms and predicate symbols, I build atomic formulas. And these are, I didn't say one thing, terms denote things in the world. So John denotes somebody who is sitting over there, let's say. Wife or father of X will probably denote the lady, okay, in the world. Now, atomic formulas refer to simple facts, denote simple facts, and they are written like term equals term. For example, John equals elder son of father of John, or predicate symbol and then a list of terms, like happy John, or lives John London, or arrives John Athens Monday, okay, and so on. And from this machinery that I presented up to now, you build what I usually called goofs, and you have to be able to say it like a dog, goof, okay, a well-formed formula, okay? And these are the most complex kind of expressions. So if I want to say I'm in a room and somebody's sitting near me and as soon as I get up, he's going to punch me or something like this, you express this right in a well-formed formula, okay? So well-formed formulas can be atomic formulas, well-formed formulas in parentheses. You can use negation, you can use a binary connective, and you can use quantifiers as well. So, for example, you can write things like Manolis is a fan of Olympiakos Piraeus. I have to fix this, sorry. Tony is not a fan of Liverpool Football Club. Tony, now here we don't know. So we don't have a complete knowledge, so we say that Tony is a fan of Man United or Man City. And for Manolis, for example, he's a fan of both Man United and Olympiakos. And then here's another formula that says, if X is a sports car and Mike has driven it, Mike's like it. I mean, Mike doesn't have much of a taste, let's say. And here we say there is X, which is a sport car, and John is the owner of it. And you can build very, very big things that describe the world using the syntax that I just showed you. And once we have the syntax, so these things, because we use English, might mean something to us. But if I was using letters like X, Y, P, Q, you wouldn't know what they mean. And then semantics come and tell you that Manolis is this person. Olympiakos Piraeus is, you know, the famous team that won the Conference Cup. Well, I would have said that, right? Same with the rest of the things that you see here. Okay? So, and if you have taken a course in logic, so this is today just an introduction, a very, very simple introduction, you would talk about the notion of interpretation, the notions of satisfaction and truth, the notion of entailment, and the notion of validity. I will define these notions very quickly and informally. So what is an interpretation? An interpretation gives meaning to a given set of formulas, okay? It maps each constant symbol to an object in the world. So for example, I say John, right? I might refer to John Lennon. Or I might be a historian, and by John I refer to King John of England, who was a king from this time to this time, okay? Now, a predicate symbol refers to a relationship in the world. So when I write brother, this, that, then I might refer to the notion of brotherhood. So again, in the world of kings of England, King John is the brother of Richard the Lionheart, and vice versa, of course, because brother is a symmetric relation. The equality symbol is always interpreted as identity, and function symbols we typically interpret through functions. So if I write father of, I might refer to the biological fatherhood. And then come the symbols for all, exists, not, and, or, implies, equivalent, or implication and double implication. And these are interpreted in the usual way, the way that you understand, okay? So if you say for all, if you write the universal quantifying, you mean for all the objects in the world, and so on. So you might write, for example, current US President Joe Biden, previous US President Donald Trump, and then you might write something like for all X, for all Y. If current US President X and previous US President Y, and I should have written an X different than Y, then hates XY and hates YX, okay? And how do we interpret now this? What is a proper interpretation for this? This is a proper interpretation for this. I mean, I show the people, and I'm telling you that, you know, the guy over there is Donald Trump, this is Joe Biden. Joe doesn't show it, but the other guy shows it that they hate each other. And somehow we also have to say that they have been, you know, the current US president and the previous US president. Okay, once we have all these things, the interpretation is okay. So interpretation is a mathematical object, but you can specify it also informally. And then comes satisfaction and truth. So what is true in an interpretation. So in logic, we don't say, is this true? We say, is this true in an interpretation? So current US President Joe Biden is in the interpretation of things in the US that we have in our minds now, okay? I think this will change pretty soon, right? And then what is entailment? We write, if KB is a set of formulas, we write KB entails alpha if for every interpretation that satisfies KB, this interpretation also satisfies alpha. This is the notion of entailment. So actually you can show using the formal machinery that I haven't shown you that from the KB that I just showed you, this entails hates Donald Trump, Joe Biden, and vice versa. And of course, since we are people interested in computers and not just logics, because we want to use computers to implement the logics, immediately the question that comes up is there an algorithm to decide the entailment? And if yes, what is the computational complexity of this algorithm? And can it be efficiently implemented? We will try to answer these questions soon. Before I continue and move to the third ingredient of a logic, notice how we want entailment to behave. So if we have a set of sentences, and sorry, let me start the other way around. If we have a world, and then something happens, and then something follows from that situation, so if I have this, and I throw it to Christina, okay, and Christina catches it, okay, the world changes in that way. If I represent here that I'm holding this and throwing it, then it has to be entailed that the thing went to Christina and Christina caught it. If we have, the proper axioms, how things move, how fast is Christina, and things like this in the original set of sentences. So whatever things are entailed have to follow what happens in the world, otherwise we're wasting our time, right? Okay. Another notion, interesting notion, is validity. So a sentence is valid if it is true in all interpretations. In some sense, valid sentences are not very interesting, right? Because, for example, the first sentence here, it says A or not A, right? And the second one basically defines implication. But they are still a pretty good set of sentences, and we can use them, and validity is an important notion. So, syntax, semantics, and then we need to define how we do inference, whether there is a mechanistic way that we can start with a set of sentences and prove another set of sentences. And then, if I give you such a way, an algorithm, I might also ask you, or rather, I would be very happy if you can do that, or you would be very happy if the algorithm that I gave you has these properties, the property of soundness and the property of completeness. What does sound mean? Sound means if I take a set of formulas, do my tricks, and something pops out, it better follows logically. It better be entailed from the original set of sentences, given the semantics, okay? This is soundness. And what is completeness? Completeness is whatever is entailed, it can be proven. Completeness is harder, as you might expect. And typically, we define a proof theory to be able to do this. And proof theories consist of inference rules. And one important inference rule is the resolution inference rule in AI, okay? It works with disjunctions. So it basically says, let me first say something more basic, that inference rules are typically written as fractions, okay? And we have some things on the nominator that are the assumptions, and in the denominator, we put what we conclude. So this basically says, the resolution says, if you have this disjunction and this disjunction, and there is a disjunct Pj and a disjunct Qk, and they unify. What does unify means? And not only unify, but they are also, one actually unifies with the negation of the other. So one, let's say, is P of A, where A is a constant, and the other is not P of X. If we substitute X, which is a variable by A, then we have P of A and not P of A, they become the same modulo the negation symbol. Okay? So all these things you have to specify formally. You have to give a unification algorithm for finding this and so on. But the idea is very simple. So if we have this, so if we have, let's say, P and not P in the simple propositional logic kind of way, then you can infer a very big disjunction where you have thrown away Pj and Qk because they cancel out, right? P and not P cancel out, okay? And you can infer the very big disjunction without these. If it's a first order formula, you have to commute the unifier, and then you have to substitute this when you do the inference. But the big story is what I have just said. And some bracket here is hidden. Okay. So for example, you might want to use resolution to prove the following, that from these formulas, we can infer rich me. Let's look at the formulas. They say, if you have a PhD, you are highly qualified. If you don't have a PhD, you make money early. If you are highly qualified, you are rich. If you make money early, you are rich. So me is like Manolis. I can infer from here that I'm rich. You can see it, right? I mean, because you either have a PhD or you don't have a PhD, and in both cases, you are rich. In both cases, you make money, and in both cases, you are rich then. Yeah? So you can prove this by resolution, by step. Essentially, the way it works, if we want to prove phi, this is phi, from the KB, this is the KB, then what we do is we take the negation of what we want to prove, we put it together with these things in a bag after these things then transform into what is known as conjunctive normal form. That is a set of disjunctions. Here they are. And then we apply resolution repeatedly, the rule that I showed you earlier. For example, you might say, I have not rich me, and I have this disjunction as well. Notice that rich X and not rich me, if I substitute X with me, become contradictory, so they can be thrown away, and I infer, not early earnings X, but I have to do the substitution of the X, so not early earnings me, okay? So don't copy this without the not. And of course, if you want, there are provers, right? So there is prover 9, for example. Now this link doesn't work, or at least it didn't work last night. You can pick up prover 9, it's a resolution theorem prover. You can throw formulas into it and prove theorems. So, we are doing inference in first order logic. Are there sound and complete inference rules? The good news is this is Gödel's completeness theorem, proven in 1930, that you can do that, okay? It might be a bit, take forever or whatever. I mean, as computer scientists, we are interested in these things, but this is not what Gödel was interested in. You can do that. So if something is entailed from a KB, then you can prove it and vice versa. And you can then see as a corollary that to check entailment or validity and satisfiability or provability of a first order formula from a set of another set of first order formulas is recursively enumerable. Now I have to stop here for a minute and give you two definitions. I will talk about, for the next couple of slides, I will talk about recursive problems or decidable problems, and recursively enumerable or semi-decidable problems. So what is a recursive or decidable problem? A problem, a yes-no problem, P is called recursive or decidable if there is an algorithm that given an input X, it tells us yes and terminates whenever X belongs to P, and no and terminates whenever X doesn't belong to P. So decidable is the best thing that we can have, right? We have the box, the algorithm, we give it something, says yes or no, and terminates all the time. Perfect. But life is not like that. I mean, in life, you also have problems that are semi-decidable or recursively enumerable. In that case, there is an algorithm that when you give it an input X, it outputs yes and terminates whenever X belongs to P, but it may commute forever when X doesn't belong to P. So essentially what the algorithm does there, it works, right? And it hasn't given you an answer. So you don't know. Maybe it has gone into an infinite loop. Maybe the next minute it will give you a positive answer. So you don't know. It's a semi-decidable thing. And unfortunately, I'll come to semi-decidable in a minute. Now we are talking, so maybe I should have organized this a bit better. So this is what, forget this for a minute. So this is the good news. First order logic is complete from Gödel's completeness theorem. But there is also the incompleteness theorem of Gödel, again proved the same year, that says that for any set A of true sentences in number theory, and in particular any set of basic axioms, there are other true sentences of number arithmetic that cannot be proved from A. So Gödel basically said, give me a number theory. I will construct a very big formula for you. You can verify that it's true, but you cannot prove it. So it basically destroyed the world of Hilbert. Hilbert was a famous mathematician who meant to build something that would allow us to prove all mathematics formally and verifiably. Yeah? Simply doesn't work. Okay. Let me now move to decidability and semi-decidability. So, unfortunately, other people also, like Turing and Church, independently, 1936, they proved that the inference problem for first-order logic is recursively enumerable. Semi-decidable, not decidable. And actually, to prove semi-decidability, you don't even need everything. You just need a binary predicate symbol and the symbols of like quantifiers and binary connectives and so on. You don't need function symbols. You don't need more comprehensive predicates and so on. It's very sad. This is sadder, of course, but this is disappointing also. But not so much, because we are positive people. Okay? So if you take monadic logic, for example, so assume that all you want to talk about is classes and their instances. And you do that in logic. You say, for example, Manolis is a person. Olympiakos is a football club. But you do not want to say Manolis is a fan of Olympiakos. You don't have binary predicates. If you only have unary predicates and the full machinery of first-order logic, this is monadic logic and it is decidable. Okay? If you have data log, I'm not going to introduce that now. This is decidable also. Most description logics that you will see in a minute are decidable. So we don't die so easily, right? If something is semi-decidable, then we try to look at subsets that are decidable, and then we work with them. And not only that, then we try to find subsets that are efficiently implementable. We have algorithms for them that are efficiently implementable, and this is even better. Okay, what are description logics now? I have not written this. I will write this again. Description logics are subsets of first-order logic with a particular syntax and semantics, and they are, you might want to say, object-oriented logics. They allow us to talk about objects, properties, roles that these objects fill, all that you would have in an object-oriented network, in an object-oriented system, you can define declaratively using a description logic. They started in the 80s and 90s and have continued up to now with lots of theoretical work, very good practical work also, and they have been used as the foundations of ontology languages, like OWL. I'll explain what ontologies and ontology languages are in a while. So what is the syntax now in description logics? So I state again clearly, they are subsets of first-order logic. So you don't need them as subsets. You can do the same thing just by first-order logic. But by introducing an alternative syntax and then alternative inference rules and proof procedures, you can do things more efficiently. So that's the idea, okay? So the syntax in this case, I will now go a little bit slower because who has experience with description logics? Not so many. You should come to our department and take my course, Knowledge Technologies. So, 3 disjoint alphabets of symbols. Concept names. Concept means class. You can understand it as class. So class names. Role names, you can understand it as relationship names. And individual names, you can understand it as object names. Okay? Now, we use these symbols to build more complex concepts and more complex roles by using conjunction, disjunction, negation of concepts, value restrictions, and number restrictions, and other things. And then we write axioms. I will say axioms in a minute, so I shouldn't have said sentences here. We use the machinery that I just mentioned to write things that describe what holds in a world that we want to represent knowledge about. So let's give a few examples. So this is my vocabulary. I have concept names, person, male, female, doctor, Greek university. Role names, has child, is alumni of. And individual names, Anna and John. Okay. Then I can define complex concepts. I can say, for example, person and not female. What does that mean? A complex concept describes a set of individuals. So these are the objects in my world that are persons and also not female. Okay? I'm one such person, for example. This is another complex concept, female or male. So this is how we use, this is the kind of conjunction that we use, this is a kind of disjunction. So this is, I suppose, it used to be everybody. Okay? Now look at this. This says, we read this, all has child male. Okay, now, this is the set of objects such that all their childs are male. How about this? This is the set of objects that have a child who is male. How about this? This is all objects that have three or more children. This is all objects that have 3 or more children that are male. This is the set of objects that have 3 or more children, and they themselves are male. So it takes a little bit of familiarity with these things to understand the notation and everything, but after that, you can be comfortable and understand even things like this. I will look at the last one. Female and, okay, so this is, okay, this complex concept represents the set of objects that are female and they have 3 or more children that are doctors and the children, right? All of them have finished Greek universities. Very complex things, right? You can define them in first-order logic also. I mean, it should be obvious to you because all we have here is unary predicates and binary predicates. But this is a more compact notation, and then comes the semantics also that is more compact, and we have a nice object-oriented logic. We call it, of course, description logic. And we can use these complicated things to write axioms. So we can write, for example, that a woman is defined to be person and female, and Greek university alumni. So here, woman and Greek university alumni are new class names, right? And how is this one defined? Person, and there is a Greek university who this person is an alumni of. Similarly, we might write things like this, that whoever is a man is a person, whoever is a man is not a woman, and whoever is a male is not a female. Okay? Now, axioms like this, in description logics, we say that they form the T box, the terminological box, because they define our terminology. It's the schema, if you want to talk databases. Okay? And in addition to the T box, we have the A box. Now, the A box is the database, if you want to talk again databases. In the A box, we put assertions about individuals, and these assertions are either membership in classes or what roles they fill. So we might say, Anna is female, female Anna. Has child Anna John. Anna is person and not male. John is male and has 3 or more children. John is a Greek university alumni. Anna is, has 3 or more children who are persons and have finished, all the universities they have finished are Greek universities. Now, the examples that I just showed you, that you have just seen, are from a description logic that it is called ALCQ. Description logic researchers have the bad habit of having long names of logics that mean something, and then shortening them to something smaller. And you have to know the jargon there. okay? You can define the semantics. I'm not going to show you this. And also a proof theory based on tableaus. You can have tableaus for first-order logic also, but in description logics, this is the way you do the proofs. You don't do resolution, typically. You do tableaus. And there are some nice reasoners also, very efficient. Although in general, as we will see in a while, the complexity can be exponential of many description logics. There are efficient reasoners like Hermit, for example. Now, description logics are used to define ontologies, or can be used to define ontologies. And what is an ontology? Gruber defined this in 1993 by saying that an ontology is a formal, explicit, shared specification of a conceptualization of a domain. So I have a domain. I have a domain, for example, of the summer school here, and I would like to write things about it, right? I can use a description logic to do that. I can use first-order logic to do that. And this is the ontology. Formal, explicit, and then if we also have a way to share it, that would be nice. For me to give it to another system to read it, for example, and so on. One can use graphical notation for ontologies. So if we want to talk about motor vehicles, for example, we have a class motor vehicle, and truck is a motor vehicle, van is a motor vehicle, passenger vehicle is a motor vehicle, and then a minivan is a van and a passenger vehicle at the same time. And we can build such hierarchies, and such hierarchies are useful in biology, in the science, in many application domains. And as you might expect, not only we have graphical notation, but we can use formal logic-based languages, for example, first-order logic to represent ontologies, but typically these are the kinds of formalism that have been used to represent ontologies. Once upon a time, there were semantic networks, then there were frames, then came description logics, and these gave birth to OWL2 and other ontology languages, and this is the area of the semantic web if you want to check it out. So this is an example, for example, of an OWL2 ontology. It's a textual syntax that you can use to enter the ontology in a reasoner, yeah? And of course, there are visual tools also to build the ontology. Protégé is the most famous one, and so on. So you can write, for example, that father is a subclass of the intersection of man and parent, or that parent is equivalent to all these that have a child that is a person, or that has father is a subproperty, sorry. So if you have has father that connects two objects, and the second object then is connected with the third one via has brother, then the first and the third are connected via has uncle. I mean, if you think about it, there is this transitivity, right? Has father this, has brother this, so this thing is a nephew of this third person. Or you can have negative object assertions. You can say that Bill doesn't have daughter Susan. Okay. What is the computational complexity of these things? We didn't say, of course, what is the computational complexity of subsets of first-order logic. We just said that they are decidable, but let's talk about computational complexity. Again, the sad thing with computational complexity is that a lot of things in AI and a lot of things in logic turn out to be exponential, and this is the case with many description logics also. For example, the description logic on which OWL2 is based. But, again, there are what we call profiles. There is, for example, the EL profile. The sentences that I showed you here are from the EL profile. Sorry. And these profiles have polynomial time complexity for the reasoning problems that are interesting. So for entailment, for example, and so on. Okay, so there are some interesting complexity ideas in this area that one can look at. And from ontologies, I naturally go to knowledge graphs. Now, what are knowledge graphs? Knowledge graphs are like the A boxes in ontologies in their simplest form. So, in fact, a knowledge graph is a set of triples SPO, where S the subject, P the predicate, and O is the object. And if you don't want to write a triple, you can write an arc, S, put here P, directed arc to O, and with these directed arcs, you can build a graph. So this is why these creatures are called knowledge graphs, and they can represent statements like, for example, Manolis teaches AI. Okay, and we might have the following triples, like Manolis is professor, AI is a course, and Manolis teaches AI. Now, knowledge graphs are important because they are used today, okay? Maybe you don't like logic, maybe you like very simple things like knowledge graphs. They have a lot of applications. The most popular knowledge graphs are DBpedia, Yago, and Wikidata that are open source. You can check them out. But search engines also have their own knowledge graphs, like Google, for example. And we can use them in search engines. So if we, or rather they are used by search engines. So if we write, for example, today in Google, what is the height of Mount Olympus, we get an answer. Now, in the old days, when you guys, let's say, have not been born, when search engines first came into existence, for such a question, they would return links. And you would click a link and find the height of Olympus. Now it returns an answer. Or we can say, and the reason it returns an answer is because in the knowledge graph you have these triples. You have that Olympus is a mount, and Olympus has height, this number. Okay? We might want to ask, which countries border Greece to the north? And we get a nice paragraph explain this to us. Now here we need a little bit more functionality for answering with a paragraph, but the idea is the same. Yeah. Now, an interesting research problem is to try to push this question answering functionality to its limits, right? So now I write what countries border Greece to the north and have population greater than 10 million, and now I get a link to Greece. Because Google understood that I want to learn the population of Greece, and it just didn't know how to answer. So I say, okay, today we also have LLMs. So I'm moving quickly now, right? Logic is no more, yeah? So I move to LLMs, yeah? So I try Gemini. And Gemini says, Greece borders only one country to the north, Bulgaria. Oh. And then while Bulgaria has a rich history and culture, its population is currently less than 10 million, okay? There are other several countries north of Greece with populations over 10 million, such as Albania's northern neighbor, Serbia. Okay, we'll fact check these things in a minute. I give it to ChatGPT also. ChatGPT says the countries that border Greece to the north and have populations exceeding 10 million are Turkey, to the north. Thank God, no. In any case, it says, you know, to the east of Greece, but blah, 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 right? So Turkey is okay. Bulgaria, over 10 million? We'll fact check this. So, Bulgaria, no, 6 million something. Serbia, no, 6 million something. So then we come to the open research problems, yeah? There has been a lot of work on question answering over knowledge graphs. The domain is still open, especially now that we have LLMs. And essentially, the domain, the combination of LLMs and knowledge graphs is a very interesting question. So that could be the subject of another presentation. I'm giving you a link here. And of course, combining logic with neural nets is also another interesting idea, and this is the subject of the next talk, if I understand correctly. I didn't have a slide for thank you, but I thank you very much.
Thank you, Manolis. Any question?
So, thanks for the talk. You seemed to imply that the LLM should be using the knowledge graphs to be able to produce more accurate responses, but who populates the knowledge graphs? I mean, people also use machine learning and recently LLMs to also populate the A boxes of knowledge graphs. So how do you know that?
Only do it like Wikidata does it, like it's a community.
Right, and you check it.
Process and all that. And hopefully this is right.
And also when you translate from the queries in natural language to some query language of your knowledge graphs, how do you know that the translation is correct also? So I'm trying to say that, you know, you can still get noisy responses.
Yes, for sure. Other questions? Please. Do we have a mic?
Because I did some programming, I would like to ask if in order to express logic propositions, you use like Boolean expressions, Boolean algebra, like true, false. I mean, in the form, for example, you can say in programming, if x greater than 1, print true. I mean, usually if then, and all that, if you want to make to translate it in a programming language like Python or something. Yeah.
What was the question?
Yeah. The question is if, in order to translate these logical expressions, logical propositions to programming language, using like Boolean algebra, true, false, true or false.
You need more than that because you.
Okay.
You need more than that because you also have a domain, right? I mean, if it was just propositional logic, that would be easy. But for first-order logic, you need more than that. But you can use a programming language is a very expressive thing. So you can use it to program things like this.
Yeah, I'm just on because I've seen that as you know, as do some programming with sometimes with very simple examples. The one I said, and
you will see something similar, but of course in the programming language you don't have the inference to be able to draw the conclusions and all that.
Okay. Yeah. Thanks a lot for the answer. Thanks a lot.
There's a question.
Thank you very much for the presentation. I would like a little bit more abstract question, but it took me there with your when you its own logic and concepts and roles and that, and it made me think a little of the unconscious of the human mind. Do you think it's structured like that? A bit like the logic that you try to describe. Do you think we're trained and all of this? A bit as you described. I don't know.
Well, come on. I mean, mine was a very practical, very simple talk. I mean, I cannot do philosophy now. But, you know, there is these things can get you to, you know, the difference between symbol 1 and symbol 2, as we say sometimes, where symbol 2 is the more deliberative kind of thing that you need a reasoning mechanism. I mean, you think, you see what follows from that, and then you take an action, right? Where symbol 1 is something different. But that's the most I can say. I'm not a philosopher. Sorry.
Thank you.
Okay. Another question? No? Okay, I would like your comment on, we know there were, and there are, some big efforts on building large knowledge graphs, so big models. There were in the past, before, even many years before, you know, GPT and these foundational models. And the story continues until today. So what you think is the future? We have, today we have the hype with GPT and this thing. So there will be a combination, I mean, of the technologies. What do you see the future is?
I hope there will be a combination, but certainly the two strands of research will also continue independently, and who knows where we're going to go. I mean, currently LLMs, of course, have the upper hand. Let's see how it goes. But I think the combination is a very interesting domain of research, for research at least. And let's see what comes up. Yeah.
Yeah, sure. Thank you. No questions? Okay, let's close this. Thank you very much, Manolis.
Thank you.